Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics, and we're in chapter 4, part of this playlist that I'm calling Joint Distributions. In this video, we're going to look at the discrete bivariate distributions. So in many experiments, two or more random variables will be considered simultaneously. The joint probability distribution of the two random variables is called a bivariate distribution. Of course, this could be extended to multivariate distributions, but we're going to look at bivariate or joint distributions. So the discrete bivariate density is this. Let x and y be discrete random variables. The ordered pair, x comma y, is called a bivariate random variable. Now the function f, and if there's any doubt, you put little subscripts, x and y, is called the joint density for x, the ordered pair xy. And it's defined as this: f of x, y, is equal to the probability that x is equal to some value, little x, and y is equal to some value, y. Now, usually we leave out the and we just put a comma, and this is what it means. And is also intersection, but it's almost always written like this, or just called f. Now, necessary and sufficient conditions for a function to be a discrete bivariate density are this: that every possible x and y value, f returns a value of 0 or more, so non-negative. Also, that when it's summed over all x and all y, it equals 1. Now here's a simple example. It's not uncommon to present a discrete bivariate density in table form. Now let x be the outcome of the flip of 3 coins. Let y be the outcome of the roll of a die. The ordered pairs xy in the following table present the joint density for x and y, defined as this. So if x is the number of heads in the 3 rolls, it can be 0, 1, 2, or 3. The outcome of a die is 1, 2, 3, 4, 5, or 6. And these probabilities, for example, 1 over 48 is the probability that we observe 0 heads and a 1 on the die. The probability that we see 2 heads and a 3 is 1/16. Now, the marginal x and marginal y means we're adding up the values across the row to become this. And we're doing it in each row. And then it ends up what's called the marginal of x. So if we just think about x, so the number of heads observed in 3 rolls, this is the probability. So the probability that we see 0 heads is 1/8. The probability of 1 head is 3/8. 2 heads is 3/8. 3 heads is 1/8. And notice those add to 1. And that's called a marginal distribution of x. And to find a marginal distribution of y, you add column, the probabilities of these by column. And they all add to 1/6, and that's what they should, because the probability of observing any number on the roll of a die is 1/6. And notice that those add to 1. And that leads us to a discrete marginal distribution. So let x and y be a discrete bivariate random variable with density f. The marginal density for x is f of x is given by this. So it's the joint density. Now some call this probably mass function, but it's 100% okay to call it a density of the discrete type. And so I'm going to call it a density. So if you take the density and sum out the y values, that leaves the marginal of x. And so the little x means for a specific value, right? So for a specific x, if we sum out the y, we get the density of that x. So for instance, let x be, say, 2, 2 in this case, and we sum over all y, we get 3/8. And so that's the density for x when x equal 2. And it's just the opposite for the marginal density for y. Let x and y be a discrete bivariate random variable with density f. The marginal density for y, f sub y, is given by You take the joint density and sum out the x's, and then that leaves the marginal density for y. Now, independent random variables, let x and y be a discrete bivariate random variable with density f of x of y sub x y. The marginal densities f sub x and f sub y. X and y are independent of the random variables if and only if the joint density is the product of the marginal densities. Now, to check independence in a table, the product of the marginals should equal the table cell entry. So let's go back up to this table. If we pick a cell, so this one here, when x is 1 and y is 5, the probability is 1/16. Now the marginal density is 3/8 and 1/16, and 1/16 times 3/8 is 1/16. So that product works, but it has to work for every entry in the table. So this 148 needs to be the product of 1/8 and 1/6, and it is. And the same over here. This product needs to be 1/6 times 1/8, and it is 1/48. And then you notice that it is independent. And if you think about it, we're flipping coins and flipping a die, so they should be independent. And this table just tells us that indeed they are. Now, an example, let x be a positive integer, be a discrete random variable with probability that x is that integer with this probability, 1/2 to the x. If x is observed, a coin is tossed with the probability of e to the minus x of a head. So it's the probability of a head is e to the minus x. Let y be the result of flipping a coin. So the values are 1 if it's a head and 0 if it's a tail. So it's a Bernoulli. We want to find the probability that we observe a head. Well, here's one approach to calculate this. We want to find the probability that y is 1. So then we introduce a variable, but then sum it out, right? Because if you think of it going backwards, we have a joint density and we summed out a value, summed out a variable, we get the marginal back. And so it works both ways. Well, this is a conditional probability. It can be thought of as conditional probability. Probability that x is, and the probability that y given x is this. But we know this. This is the probability of observing that integer, which is 1/2 raised to the x. But given the number, the probability of a head is e to the minus x. And now the sum comes down. We join these, right? And it becomes this. But this is less than 1, so it's a geometric series. And there's a specific limit of this. That simplifies to this value. And that equals 22.5%. So there's a 22.5% chance that we observe a head. Now let's do a quick simulation of this to see if that's the case. Now the tricky part of simulating this is picking the integer. Remember that integer has a probability of 1/2 to the x. So the probability that it's a 1 is 1/2. The probability that we observe a 2 is 1/4. The probability we observe a 3 is 1/8. Probably, etc. So that's the tricky part of this simulation. So we're going to call this function coin.flip because we want to flip a coin and find the probability that it's a head. And it's going to take a few steps. So we found in is no, meaning we need to observe that random variable, and currently we haven't seen it, so it's no. We're going to arbitrarily put a 1 in for x because, yeah, you'll see. So then we generate a uniform random variable from 0 to 1, and that's called temp. Now, if temp is between 0 and 1/2, we're going to let x be 1. If it's between 1/2 and 3/4, then we're going to let it be a 2, and then we're going to, so we're going to incrementally find it based on this random number. The cutoff is 0, so we're going to start at 0, right? And the first one, when x is 1, it's from 0 to 1/2. So, and then we check to see if the random number is less than 1/2. If it is, boom, we found our integer. It's 1. So that we count it as yes. If no, we keep moving across that uniform, the interval from 0 to 1 until we find where that random number is, and then we base our integer off that. So we add 1 to n, and we look at the cutoff. So now, remember, we stored a half in cutoff, so it's a half plus a fourth, which is 3/4. So now if the random number is less than 3/4, we've found our integer, and it's 2, right? And if not, we keep going until we found the integer. And then once we find the integer, then we need to flip a coin based on e to the minus x. And we generate another random number. And if it's less than that, boom, it's ahead. If not, it's tail. And then we print out our results, the n, and whether it was ahead or not. We're going to do this 1,000,000 times. So we're going to use sapply from 1 to 1,000,000. We're going to flip the coin, and we're going to store the results in results. Now let's look at row 1, which is the random integer that we picked. And then we also print out the theoretical. So we should observe a 1 50% of the time, and in our simulation we observed it pretty close to 50% of the time. We should observe a 2 1/4, 25% of the time, and we theoretically, or in the simulation, is pretty close. 1/8 of the time we should observe a 3. It's pretty close. And if you notice that we do, and actually in this simulation we went up to a 20, based on that random number. Well, let's print the results. 22.5% of the time we saw ahead in our simulation of 1,000,000 reps. And notice that the theoretical, as we proved in the example, is 22.5. So it's really, really, really close. Okay, so we're at 12 minutes. I need to stop. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.